If you're at station 1 and you are about to do determining molar mass of a gas, this is the setup you have. You have a graduated cylinder filled with water, and then somehow you have to move it into the top of the water without spilling any. You have a thermometer, a balance, and a barometer on the wall to measure the pressure. The butane lighter you should wait before with the plastic tube. Then once that's done and you write your number down, go here, collect your gas. So these are examples of just numbers. I made up the numbers, and then you actually are going to do your own lab. The gas was measured in milliliters, and it's analog, so I'm taking the smallest reading as its absolute uncertainty. The thermometer is digital, so it's the last digit is uncertainty. Barometer is digital, 0.01. And the mass, notice I'm going to subtract two numbers before and after. So the absolute uncertainty is the sum of the two individual uncertainties. I'm also giving you theoretical value of the butanes, so we can use it eventually to calculate our percent error. Now let's just crunch some numbers. So first I'm going to, for each absolute uncertainty, I'm going to convert it to relative or percent uncertainty. We take the absolute, divide it by the number times 100, and you see this is what I did for the volume. Same thing I do for thermometer reading in Celsius. I do the same thing for inches of mercury for barometer, and I do the same thing for the balance for the grams. Then next thing is to convert units. I converted in order to be able to use my gas constant 8.31 joules per mole per Kelvin. So I'm going to convert my milliliters to decimeter cube or liter, but the absolute uncertainty stays as is as the original one, as the measured one. I convert my Celsius to Kelvin, and I keep the absolute uncertainty as it was. I convert inches of mercury to kilopascal, and then I'm going to keep the absolute uncertainty as is. Grams, you don't need to do anything. Now we are ready to calculate moles, which is pressure times volume divided by gas constant temperature. Three significant figures, and this is moles of my gas butane. Then I'm going to calculate molar mass, which is nothing but mass divided by moles, and this is what I find. And since this is according to the experiment, this is experimental value. To calculate percent error, you have to remember there is an absolute value for it. It's theoretical minus experimental divided by theoretical times 100, and I get 16.7%. The next calculation is what is the total uncertainty. So we are going to add the individual measured one for the volume, for the temperature, for the pressure, and for the mass. So the total percent uncertainty is due to random error, and the instrument is 9.4. Now we are going to make a judgment. Since percent error is bigger than percent uncertainty, then we have combination of systematic and random. And for your information, because this will take place in many questions, random errors can be reduced by means of repetition, repeating the trials, but the systematic, you have to get lucky and remember what to remove, such as calibration of an instrument. You also can reduce random errors by choosing more precise measuring devices. So you should use this example in order to apply your own numbers and make a judgment about your own lab.